Okay, this is discussion 4.2 for IB1 on covalent bonding and molecular geometry. So, we're going to talk about differentiating ionic and molecular compounds in terms of properties. We're going to name molecular compounds and draw their structures. There is a lot in this discussion that's kind of hard to do via video as far as drawing the Lewis dot structure, so if you need more help after you watch this, just find a time to come and see me. Okay, so we're going to talk about properties of ionic and covalent compounds, and we're also going to talk about metallic substances here too, just to give sort of a point of comparison. We say metallic substances because this applies to metals that are elements and compounds. So ionic compounds contain a metal and a nonmetal, and molecular or covalent contain two or more nonmetals, and metallic compounds and substances obviously contain metals. So it's helpful when you list their properties to think about common examples because you might struggle to come up with random properties of ionic compounds in general, but you certainly wouldn't struggle to come up with properties of table salt. So examples I recommend, for ionic compounds I suggest you just use sodium chloride, which is table salt. For molecular compounds, I think it's helpful to have a few examples because their properties can vary a lot. So I suggest carbon dioxide, water, and sugar would be good examples. And when you think about metallic substances, you could think about anything made of metal, so copper wire, brass, etc. State of matter at room temperature, again, with those examples in mind, it's very easy to answer that question. Ionic compounds would be solids. Covalent or molecular compounds could be solid, liquid, or gas, and metallic substances are usually solid. A notable example is something that's not solid is mercury, but generally they're going to be solids. Okay, so talking about some other properties. As far as their conductivity in the solid state, ionic and molecular compounds are not conductors, but metallic substances are, hence why we make wires out of metal and not salt. In terms of solubility in water, ionic compounds typically dissolve in water. Molecular compounds sometimes do, just depending on their properties. Metallic substances do not. That's why we make buildings out of metal. It would be very bad if they dissolved in water. And there's a few exceptions to that, but most common metals do not dissolve in water. As far as their conductivity when they dissolve, ionic substances are conductive. Molecular substances are not, and since metals don't dissolve in water, that's sort of not applicable here. Ionic substances have very high melting and boiling points. If you think about trying to melt salt, you've never done it because they have very, very high melting points. Molecular compounds have relatively low melting and boiling points, and metallic substances have high melting and boiling points, but generally not as high as ionic compounds. In terms of electron behavior, ionic compounds transfer electrons from a metal to a nonmetal. Molecular compounds share electrons, and when we talk about metallic substances, we talk about this analogy called the sea of electrons. The idea is that we have sort of free-moving or delocalized, so delocalized, not stuck in one place, electrons, and this actually leads to a lot of properties of metallic substances, notably conductivity. So what holds ionic substances together? That would be charge. If you want to be super fancy, you could say electrostatic forces. Covalent compounds are held together by the shared electrons in covalent bonds, and metallic substances are held together by the attraction between the delocalized electrons, or free-moving electrons, and the positive metal nuclei. When we describe their structure, for ionic compounds, remember we talked about the crystal lattice, where the oppositely charged ions are being held together. Molecular substances are individual molecules, and if we were asked to describe the structure of a metallic substance, we would just cite the sea of electrons example. Okay, so let's talk about why we have to name molecular compounds differently than ionic compounds. So a good example here is carbon dioxide and carbon monoxide. Now, in ionic compounds, if we were trying to use the simplest way to name them, we could just call it carbon oxide, but that gives us no way to differentiate. And we really can't use the Roman numerals here because that specifically refers to charge, and these are covalent compounds. There's really no charge involved. So we have to use a totally different system to name molecular compounds, and when we do that, we use a prefix and the name of the first nonmetal, and then another prefix and the name of the second nonmetal, plus that same suffix "ide" that we used in ionic naming. So here are the prefixes for molecular compounds. You might want to pause this for a second just to get all of these down. Mono is 1, di is 2, tri is 3, etc., etc. Now, one thing you might have noticed in the examples we just gave of carbon dioxide and carbon monoxide is that we don't use the prefix mono on the first word. So we don't call it monocarbon dioxide or monocarbon monoxide. We just say carbon dioxide and carbon monoxide. That is only true for mono. Every other prefix can be used on the first nonmetal as well. Why? I don't know. Maybe just to make your life hard. Okay, so I'll give you two examples, then I'll have you pause, try the rest of these, and check your work. So the first example, dinitrogen trioxide. That means there's 2 nitrogens and 3 oxygens. When we look at the formula Si2Cl6, we would name that disilicon hexachloride. Okay, so pause this, try those other 4, and then check your answers. Okay, here are the answers to those sample questions. Now, the next step is to try to name compounds when they're all mixed together, ionic and covalent. And this is deceptively tricky because even if you totally mastered ionic naming, now that you've used the prefixes for covalent naming, you're going to be very tempted to use those in ionic compounds as well. So I think it really helps, especially when you're writing the name of the compound, to just write an I or a C next to the formula before you try to name it, just to remind yourself what system you're using. So remember, we're only going to use those prefixes if it's a covalent compound containing just nonmetals. If there's a metal in the compound, we can't use the prefixes. All right, so pause this. Where you're given the formula, write the name. Where you're given the name, write the formula. And then when you're ready, you can press play and check your answers. Okay, here are the answers to those. And if you have specific questions on these, please bring them to class. The most common places that people are going to mess up are actually on barium fluoride and magnesium nitride. I think that after having learned all these other systems for naming, that seems too simple to people sometimes, like they need to throw something else in there. So that's where people have a tendency to want to use those prefixes incorrectly. So just be really careful there. Okay, so when we want to show the bonding of covalent molecules, we use Lewis structures. So dots, as you probably recall from Unit 3, represent electrons, and a bond is formed between atoms when they share 2 electrons. So we can represent a bond either using 2 dots or we can use a line. And every atom is trying to share electrons to get 8 electrons. And that's because that'll give them a full outer energy level, like the noble gases, and it's the most stable configuration. So we call this the octet rule. There are a few exceptions. The one you're going to use the most is hydrogen, and hydrogen only needs to have access to 2 electrons. The reason for this is that the nearest noble gas to hydrogen is helium, which only has 2, and that's because the first energy level only has an s orbital. Another exception you should be familiar with is boron, which can have access to 8 electrons but is satisfied with only 6. Okay, so when we draw Lewis structures, we're going to follow a bunch of steps. Now this looks like a lot of steps as you start out, but as you sort of get better at these, you're going to collapse these steps and not really do all of them. The first step is very important, and you have to do that every time, no matter how good you get at these. You have to count the total number of valence electrons, because when you draw the structure, you have to use exactly that number, no more, no less. So if you don't count the valence electrons, you're probably going to just keep adding electrons till everything is satisfied, but that may mean that you use too many. Or it might mean you use too few. Now, after you've counted the valence electrons, you want to arrange the atoms spatially so that the least electronegative element is in the center. Carbon is always going to be in the center, and hydrogen will never be in the center. Hydrogen does have low electronegativity, but because hydrogen can only make one bond, it can't be a central atom. Now, there's a lot of different ways that you could do this, and if this doesn't work for you, come see me and I can try some other things with you, but I suggest that it's helpful to connect the atoms initially with single bonds, okay? Then once you've done that, look at how many electrons you have left to work with and distribute the remaining electrons around the outside atoms first, making an octet for each element, and then go back to the central atom. Now, check to see that every atom has access to 8 valence electrons except hydrogen. If every atom does not have access to 8, that is your clue that you're going to have to share more electrons. So instead of just having single bonds, you may need one or more double or triple bonds. Now when you're finished, you want to check a few things. First, you want to count and make sure you have the correct number of electrons, and then you want to double check that every atom has access to 8. Okay, so let's work through water as a simple example. First, we're going to count electrons. We have 1 valence electron from each hydrogen and 6 from oxygen for a total of 8. So our final structure must have 8 electrons. Now, we already said that hydrogen can't be a central atom, so oxygen has to go in the center. So that's how the atoms will be arranged spatially. We're going to start with a single bond between each atom. And then we've used 4 and we have 4 left. Now, we don't need to distribute any more to hydrogen because hydrogen is satisfied with 2. So with those remaining 4 electrons, we can put them on the central atom and it'll look like that. Those electrons that aren't shared with any other atom are called lone pair electrons. So oxygen, the central atom here, has 2 bonds and 2 lone pairs. Let's look at another example that's not quite as straightforward, carbon dioxide. Now, we have to again count our electrons, and here we have a total of 16, 4 from carbon and 6 from each oxygen. Our central atom is going to be carbon. We said carbon's always a central atom, but also it's less electronegative, so we could use sort of either rule here. So that's the way they're going to be arranged. Now, let's start with a single bond between the atoms. All right, so that uses 4 electrons. That means we have 12 left. So if we distribute them to the outer atoms, once we've satisfied both oxygens, we've used all 16 electrons and we have none left. Now, there's a problem with this structure, and that is that carbon is not satisfied. So we could take 2 pairs from the outer oxygens and put them on carbon, but then the oxygens wouldn't be satisfied. So the only way to fix this problem is to use double bonds. So we'll have double bonds between carbon and each oxygen atom, and then the 2 oxygens will each have lone pairs. Now, we're going to talk about something called electron domains that are going to help us determine the shapes of molecules. So if we look at a central atom, every bond, whether it's single, double, or triple, and every lone pair around a central atom is known as an electron domain. We don't care about the outer atoms as far as counting electron domains, only the center. So if a molecule had 2 lone pairs of electrons and 2 bonds on the central atom, like water for example, how many electron domains would it have? It would have 4. When we think about the example of carbon dioxide, carbon only has 2 bonded groups. It doesn't matter that they're double bonds. Each oxygen still only counts as 1 electron domain, so carbon dioxide only has 2 electron domains around the central atom. Okay. There's some more examples in the guided notes. We did 2 of them, water and CO2, but try the other 4, and when you're ready, press play and check your answers. Okay, and I know these aren't the neatest because they're handwritten, but hopefully they're good enough for you to see. And again, you have to count every time. Now, for the carbonate ion with the charge, the only way that that's different is in counting valence electrons. So if it's a negative charge, you have to add additional electrons. If it's a positive charge, you subtract that from your total. And once you've counted them in the total, you don't have to worry about it as you draw them. Now, normally we would put brackets around that ion and the charge outside. I didn't show that here, but that's technically the most correct. I'm not going to hold you super accountable to that. Okay, so when we talk about these covalent molecules, we have to eventually talk about their shapes. And once we've drawn the Lewis structure, it's fairly easy to come up with their shapes. So that's based on something called VSEPR, or VSEPR theory, and that stands for valence shell electron pair repulsion. It's a pretty logical name. The valence shell electrons are the ones involved in bonding. Electrons are generally, we're drawing them in pairs, and electron pairs repel each other because they have similar charges. So the idea here is that all of the electron domains in an atom are going to arrange themselves so they're as far apart from each other as possible. So these electrons are repelling each other and forcing the molecule to assume certain shapes. So the number of electron domains is going to determine the shape and the bond angles. And when we talk about the actual shape of the molecule, that's known as its molecular geometry. Now, Before we go on, any molecule with only 2 atoms is linear because if I have 2 points, the only shape that can possibly have is a line. So everything from here on out that we're going to be talking about has 3 or more atoms. Okay, so if we have 2 electron domains around a central atom, like CO2, the furthest away they can be from each other is 180 degrees, right, if a circle is 360. So carbon dioxide would have bond angles of 180 degrees, and because that's a straight line, we call that linear, not very creative. Now, if I have 3 atoms around a central atom, like carbon dioxide, that would be called trigonal planar. Trigonal because there's 3 atoms around a central atom, and planar because it's flat. And those bond angles would be 120 degrees. Now note in this Lewis structure, the Lewis structure doesn't actually reflect the bond angles because sometimes when we're drawing the Lewis structure, we don't even know what the eventual bond angles will be. But because it has 3 domains, in reality, this molecule is going to have bond angles of 120. Now, let's say that we had a structure like that with 3 domains, but one of those electron domains was a lone pair. So just imagine that one of those oxygens was replaced by a lone pair. Now, you might expect that since there's still 3 electron domains, the bond angles would be 120 degrees, and that would be an excellent guess. However, they're actually 118 degrees-ish. Basically, they're a little smaller because the lone pair on the central atom is slightly more repulsive than a bonded pair. You can kind of think of it as being more concentrated on the central atom. Concentrated is not really the right word, but because it's not shared between 2 atoms, it's going to repel the electrons in the bonds just a little bit more. Now, I would actually accept a range of bond angles here, but basically the idea is that as I replace bonded groups with lone pairs, the bond angles decrease slightly with each substitution. Now, not very creatively, we call this bent because the shape looks bent. Okay, now, if we have 4 electron domains, we have 3 options. We could have no lone pairs, 1 lone pair, or 2 lone pairs. If we have 4 electron domains around a central atom with no lone pairs, the shape is called a tetrahedral. Now you might think that it would be flat with 90-degree bond angles, but remember that these domains are trying to get as far away from each other as possible. And so having a flat shape with 90-degree angles doesn't really maximize their ability to get as far away from each other as possible. It doesn't use all of the 3-dimensional space. So the bond angles are actually going to be 109.5 degrees. Now, if we have one of those atoms replaced with a lone pair, that would be called a trigonal pyramid, and the bond angles would get a little bit smaller with the replacement of a bonded group with a lone pair. So maybe 107.5, but again, I'd accept a range. And if we replace 2 of them, we would call that bent again. But note that the bond angles here are different. They're 104.5 as opposed to 118. And that's because we still have that same basic bent shape, but now we have 2 lone pairs instead of just 1. So this is a 4 electron domain shape as opposed to 1 with 3. Okay, this is a lot to take in, and I really recommend that you use, especially if you're learning this from the video lesson, make sure you look at the PhET simulation that we did with the lab, because that'll let you see these molecules in 3 dimensions, and I think that's really, really helpful. We looked at models in class, but again, if you weren't there, that's something that you kind of missed out on a little bit. Okay, so there's a few more examples. I want you to pause for a minute and try these. Remember that for nitrate, we're going to add an electron to account for that negative charge. And when you're ready, press play. Okay, those are the answers, the bond angles, shapes, and structures. So if you're really struggling with this, please come see me. This can be kind of a challenging topic and definitely one that requires a lot of practice. Good luck and come see me with questions.